Give people a second to trickle in. All right, I think we're live. Okay, welcome everyone to another episode of GPU Mode. Today I'm really thrilled. We have Perry Zhang from the How AI Lab at UCSD here to talk to us about making video models faster, video diffusion models faster. I figured it would be a nice change of pace from the typical LM stuff that we usually discuss on the channel. So Perry, thank you so much for coming, and please take it from here.
Yeah, great, wonderful. Hi guys, thank you for having me here, for giving for this opportunity to present our project of FastVideo, accelerating large video diffusion models. And if there's any mistakes made in the slides, please let me know in the comment section or just call me out. Yeah, and as the host just mentioned, today's talk will be more on the application level compared to previous talk in CUDA mode. And I'm sure people here are experts in language model inference, and I try to give people an overview of the inference workload of large video diffusion models, and including some efforts that we made in our FastVideo projects and some of the ideas that we published in our recent papers. And we may touch a little bit about the concepts of attention kernels, but not too much. Yeah, a little bit about me. So I am a first-year PhD student at UCSD, supervised by Hao, and I worked in video generation in general. And I work on the project FastVideo, obviously. I published papers like STA and VSA. And before coming to United States, I spent 5 years in Singapore and working in vision language model and language models. And I am one of the many authors of Lava One Vision, Nangva, and TinyNama. Great. So let's take a look at video generations models nowadays. And I think it is a really good time to look at them now, because they are really taking off with a very sharp upper trajectory. If you look at how the ELO score of Google's View 3 is managed to increase from View 2, that's by above 100 points in ELO. And normally for language model, they only increase the SOTA model only increased by 20 points or 30 points. So they are developing, people are developing and increasing the quality of video generation models very fastly. Many companies are working on this, Google, OpenAI, and Kling. And maybe right now its market is not as big as language models, but people believe it will one day become comparable to language model, because people believe, I mean, at least some people believe, future video generation models can become so-called word model to model the word, and which can be potentially used for agentic tasks and embodied AI. Great. So since not all audience has a background of video generation, I will firstly briefly introduce how diffusion transformer works to generate a video. And I will take this state-of-the-art open source video models 1.2.1 as an example. It's basically the same as image diffusion models, but with a much longer sequence length. Here I use, so the diffusion process takes inside the diffusion transformer, which is in this block. And this is the core of video generation models. The denoising process is conditioned on our input, which is a noise, and a user-provided prompt, and also the time step. And the time step is normally 20 to 50 times. To guide the generation with textual information, attention is applied between the diffusion transformer and the text encoders. And note that videos is in 3D, so there are height, width, and the time step, and the time dimension, the frame dimension. So when performing, transformer takes a sequence, so we need to flatten the 3D videos into a 1D sequence. And finally, a decoder decode the final video from the latent representation and produce a high resolution generated videos. So diffusion transformer works in latent space in general, which can compress the sequence length a little bit. Let's break down the video DIT inference time and see how we can accelerate them as a context. So taking Hunyuan video as an example, which is another state-of-art open source models, we can produce videos with 5-second and 720p resolutions. And the diffusion transformer will take in compressed tokens with 32 by 45 by 80, and a simple calculation will arrive at more than 100 tokens, which is a lot if you consider that it's only a 5-second and 720p videos. Consequently, the long causal attention used in diffusion transformer takes over 85% of the flops during inference. And their diffusion is an iterative process. For example, for Hunyuan, its default diffusion cycles is 50. And each forward pass of the diffusion transformer takes like 19 seconds on an H100. That is with the optimization such as flash attention 3 and torch compile. So in total, with 50 time steps, it takes 16 minutes to generate a video that is only 5 seconds on this high-end H100, which is very, very cumbersome. And the language encoder and VE takes very minimum time. And as I mentioned, attention dominates the cost. So in summary, at least existing open source video generation models are bottlenecked by two things. One is the iterative process of diffusion. The other is the attention. And we should devise methods to tackle those two major costs to accelerate video diffusion models. And there are numerous works has been proposed to reduce the diffusion time steps, including in the for image generation as well as video generation. For distillation, like methods, progressive distillation, consistency models, DMD, LADD. And note that this distillation is not from a larger teacher to a smaller student models, as in the case of language models. It is between two models with identical size, normally, from a teacher model with a large amount of diffusion time step to a student model with a very few diffusion time steps. And this distillation methods can reduce the diffusion time steps by 5 to 10 times. So it can accelerate the inference time by 5 to 10 times, which is a lot. And distillation requires training, and the training is notably very unstable. There are many successes in applying distillation in image generation models, but not so much in video generation models. There are some papers published in this area for video generations, but there's not a lot of open source code out there, and it's very hard to reproduce based on existing very few open source code. And another line of work is called feature caching. So they leverage the heuristics that in neighboring diffusion time steps. So imagine this is previous diffusion time steps, and this is the current diffusion time steps. The intermediate feature maps of transformers is very similar. So we can strategically reuse some feature maps from the previous time steps and use them in the current time steps. So we can avoid calculating some components of the diffusion transformer. Here in this plot, we are skipping the feed-forward layers for the forward pass, and we reuse the features from the previous time steps. And maybe in the other time step, we can disable the attention and reuse the attention features from the previous time step as well. And normally this kind of methods can accelerate inference by two times, and it does not require training.
Sorry, Perry, just had a question. When you mentioned something like feature caching here, like presumably if you're skipping a feed forward, you're not doing a computation, but you need to load the weights from the previous time step. So it feels like you'd become memory bandwidth bottlenecked. So is it just the case that diffusion models are typically compute bound because you're doing 50 steps?
Yeah, diffusion models is typically compute bound, and because the sequence length is very huge, so it's like over 100K. So it's definitely compute bound, but the memory is indeed an issue because you need to cache the entire intermediate features from the previous time steps. And if your sequence length is 100K, that is a lot. Consider that you have many diffusion blocks, and you need to cache the features after each like feed forward and after each attention. Yeah.
And then, so also related, like when you first mentioned progressive distillation, to me, this sounded like a form of speculative decoding in some sense, like where you basically just have, like, not quite actually. I think that analogy doesn't hold. Okay, never mind. I'll park my question.
I would say it's very similar to it's actually very similar to distillation in language model. If you consider the fact that it's just a diffusion distillation in language model is from a larger teacher to a smaller student, and here in diffusion models it's from a teacher with more time steps to a student with less time steps. So essentially, we are still reducing the compute we needed to for the same kind of performance if we can do the distill quite well. Yeah.
Okay, that's clear. Thank you.
And as I mentioned, there are many distillation methods. Many of them is applied on image models, and a few of them is applied on video models, and not all of them is open sourced. So FastVideo currently has incorporate one distillation method, which is called PCM, and one feature caching method called Tcache. And we have abstractions to add other distillation and caching methods. So we want to have a unified inference framework so people can add features to FastVideos, because currently it's very fragmented. So people publish their code in different repos for different models, and very hard to compare which methods works the best. And we have distilled a model last year. I think it's on December of Hunyuan, where we in FastVideo, and we can make it 8 times faster with a slight drop in quality. And as I just mentioned, the two major costs in diffusion transformer is firstly the iterative process of diffusion, and secondly the unproportional amount of attention flops in the DIT blocks. So we also want to have some methods to reduce attention flops, and people only start to look at this very recently, because the sequence length is only very long for video diffusion models, and it's actually short for image models, so people did not look it before, at least in the context of diffusion models.
So Barry, before we go to attention, so someone had an interesting question around. I've seen there's some labs, like for example, like TOSVid, for instance, has distilled video diffusion models that they provide, where they basically say this runs in 4 to 8 steps, and then it's extracted as a LoRa such that it's compatible with diffusers. Could you maybe talk a bit about the composability of LoRa and distillation in this case?
Oh yeah, so people use LoRa as a plug and play adapters to accelerate diffusion models. So the main application scenarios is like, so imagine I can train a distillation LoRa's from, for example, this one model, and later some people fine-tune one on some domains, let's say cartoon, and they do not distill their fine-tuned models on cartoon. They just fine-tune it, so it's still a 50 steps diffusion time steps. In that case, LoRa is very composable, because you can apply a LoRa that is trained with the original pre-trained 1.2.1 and apply that LoRa on the fine-tuned model, and it can still accelerate the diffusion transformer. And that's why I think people love LoRa. One reason is obviously it's very small. The second reason is like plug and play and very composable.
Interesting. Okay, thank you.
Yeah. So let's go into attention. So we have two papers that is either published or archived. The first one is a fast video generation with sliding tile attention that is just accepted by ICML 2024. And this faster video diffusion with trainable sparse attention is recently archived. So the reason why we can accelerate attention is because attention score is generally very sparse. And here, if we look at the left plot, which is the attention map, you can see that only very few indexed in the attention maps has a high attention score, and the rest is basically 0. And a different attention head in different layers has very different patterns. If we can have a mechanism to predict this pattern without calculating the entire attention, we can accelerate attention. And the right plot is more illustrative, which shows a 3D scenario in video. So consider this as a video. This is like the frame dimension. This is like the width dimension, and this is a height dimension. And in the middle, there's a query. And the query will attend to KVs. And here we plot the KVs that has large, significantly larger attention scores. So you can see that some patterns is like local, some pattern is global, some attention head exhibit both local and global characteristics, and some like is very intuitive, like they attend to the height and width dimension. Some attend to the temporal and width dimension, and temporal and height dimension, so on and so forth. But so the main takeaway is that attention in diffusion transformer is sparse, but they are very dynamic, and we need a method to predict the pattern. But the prediction should by itself very lightweight, so we can really accelerate the attention. And there are also some hardware constraints for attention pattern as well, which is basically the block sparse pattern. So imagine this is the attention map, and each row represents a query, and each column represents KVs. And if we have an attention map that is on the left, and it's very scattered and very zigzag, there will be 3 different kind of block. So attention works. I think people know how attention works. It's basically performs tiling, and on each GPU SM, they will calculate a single block. And if a block is dense, the GPU can compute it very efficiently. But if a block is like mixed, which we want to calculate some of the elements from it, but remove the rest, the GPU still needs to perform all the computation and later remove the unwanted result. And if a block is completely empty, we can just skip that block. So we want to predict the attention pattern like this, but we also want the attention pattern to look something on the right, which has only dense block and empty blocks. Because dense blocks can be calculated as a whole and empty blocks can be excluded. And the mixed block, if we have some mixed blocks, we are actually wasting computation. Because the mixed blocks has the same computation cost as the dense block. If we need to compute everything inside a mixed block, why not we just retain all the values out of it, right? So this is some like hardware constraints on the attention pattern. So in general, as I just mentioned, we want to predict critical tokens and only perform attention on critical tokens. And we want the prediction process to be very lightweight. So there's a prediction and actual attention cost. How much attention, how much cost, how much computation should we spend on prediction, and how much computation should we spend on the actual attention? And for efficient execution, it requires block sparse attention. And it means that we are essentially calculating critical blocks instead of critical tokens. So in the right-hand side, I have a figure to illustrate these things. So if we want to calculate the critical tokens as denoted by the red dot, we only want to calculate them. And if I have a attention block size that is 4 by 4, so I will potentially pick this block. Even though I only want this 4 dotted points, I can still retain the other attention scores, because there's no harm including them, because attention is by right full attention, and we want to make them sparse. So there's always no harm retaining those scores in this block. And the block size or tile size plays a very critical role here, because if the block size is small, we can come up with a more fine-grained attention pattern that can capture more critical tokens with the same sparsity. So the left plot and the right plot has the same sparsity. We are calculating the same amount of the blue squares. The only difference is their block size. So the right-hand side has a block size of 2 by 2. So we can then calculate all the red dot with the same sparsity with a smaller block size. But that's not achievable in the left-hand side. However, smaller block size will have a lower arithmetic intensity in attention kernels, which means the attention kernels may run slower. So there is a block size versus efficiency trade-off. We believe that a smaller block size make the attention pattern more expressive, which is good for the diffusion performance, but a smaller block size is bad for the kernel efficiency for actual speed up. So imagine the scenario where the block size is just 1, which means we can allow for any kind of attention pattern, because block size equals to 1 basically means we are no longer following the block sparse attention pattern. And then the last question is, if we are only calculating for those, for example, blue regions, which means we are excluding a lot of connections in the attention. So do we still need dedicated branches, attention branches, for global or local context? Maybe we can design some attention mechanism that is more coarse-grained, more lightweight, but it attends to every token. And maybe we can use some heuristics from CNN, where a token will attend to its neighbor. So that is the question we try to answer in our paper, Video Sparse Attention. And for efficient execution, following the pattern of block sparse attention, one very important technique used is to reorder the sequence. And this is, I believe this technique is first proposed, at least in diffusion transformer, is in our first paper, Fast Video Generation with Sliding Tile Attention. So this is a 2D scenarios. So it's not video yet, it's image. Imagine this is like VIT. Normally, when VIT deal with image, you will flatten the 2D image into a sequence. And the way video diffusion transformer, or the way VIT flatten it, or image DIT flatten it, is following a zigzag pattern. So it assigns an index row by row and column by column. One problem with this is that nearby so these two, consider this 1 and 10, they are very close to each other, but they have far away indexed in the 1D sequence. We propose to token reorder techniques that shard a 2D image into subregions with continuous indexed in each region. So here in this subregions, we have in total 9 tokens. And if we can use a block sparse attention with block size 9, also, so yeah, this number 9 is just for illustration. Normally, like attention block size has 128. So, and if we can map these subregions to a single block in attention, we can allow for efficient execution. In 3D scenarios, that means we can shard videos into very small cubes. For example, here a cube is a 2 by 2 by 2 cube. We can map this cube into a single block in the attention kernel that is continuous. And when we perform sparse attention, this entire cube will either attend to this cube or do not attend to this cube. So we can then form a block sparse attention pattern. And in reality, normally the dimension of a video for 5 seconds 720p is something around 30 by 48 by 80. And we can design the cube dimension to be 4 by 4 by 4, for example, which is actually a very small cube that corresponds to in total 64 tokens. And then map this 64 to a block in attention. And this 64 is actually a small number for attention kernel. Normally on A100 is 128. So for maximum like theoretical speed up for the attention kernel performance, we may want to design the cube to be shaped, for example, 4 by 8 by 4. And there is also a minimum block size that we can support. For example, on A100, the minimum MMA size is 16 by 16. And on H100, the minimum is 16 by 64. So the trade-off here is if we want to make the cube size smaller, we are making the attention kernel slower. If we want to make the cube size bigger, the attention is faster, but we will have more coarse-grained attention pattern, which is already illustrated in this plot. So the main contribution of VSA is a lot of ablations to help people choose what is the correct balance between attention speed, kernel speed, and the cube size, and many other design factors. I will just firstly go through the best configurations that we find through a lot of ablations for a better understanding. So a video is first partitioned into cubes with size 444, which means we are using a block sparse attention with block size 64. And tokens with within the same cube has a continuous positions when flattened into 1D sequence for attention, which forms block sparse attention pattern. And here in this plot, this is attention flowchart. This is Q, K, and V. After cube partition, a coarse branch will perform 4 by 4 by 4 average pooling for QKV to get cube level representation. We are essentially reducing the sequence length by 64. So the cube level attention is very lightweight, and we can get a global coarse-grained output. And after the attention, we need to broadcast the attention back to the original sequence length. And the attention map of the coarse attention is used to pick the critical blocks for the fine-grained token level attention with top K. So the fine-grained branch is still computing token level attention, but with sparsity. How do we decide which block to calculate or not is from the attention map from the coarse branch. And fine branch use an attention block size of 64. And in the end, we have a gate for each branch. This gate for coarse branch and this gate for fine branch. We times them with the corresponding attention output and add them together to balance the contribution of coarse branch and fine branch to get the final attention output. So far, is there any question in the channel? I can't see the comment.
Yes. So there's some questions that I think I would rather save until the end, but maybe there's one question is from Tolga Kongos, which is, do you see potential in Matryoshka representation learning in this field? They seem very data efficient, but perhaps there might be some performance concerns.
Sorry, can you repeat the question?
Let me just post it on the here. You can read it.
Oh yeah.
Yeah, we're doing.
I'm not sure if I'm not sure if he is referring to compressing the tokens. I read some papers of the Matryoshka representation in vision language model. So you can maybe compress some tokens and the other tokens. I think they are orthogonal, but I think the idea is that if you compress by a lot, your performance will degrade because we're already compressed in the VAE. So remember, we have a variational autoencoder to compress the pixels. And normally people use the compressed rate 4 × 8 × 8. And that is used by one, that is used by Hunyuan. I think the reason why, there are some papers published that if you use a very large compression rate here in VAE, it's very hard for diffusion models to converge and learn. And I will later show that our sparse attention has a better Pareto frontier than full attention. And I have some baselines to compress the K and V values as well. Yeah. So we use a block size of 64. That is obviously going to slow down the attention kernel because, for example, in FA3, I believe they use a block size of 128 times 172 or something. So if, for example, if we set our sparsity level to 87.5, which means we're only calculating 12.5% of the attention, theoretically we will have a speed up of 8 times. And in reality, with a block size of 64, we can achieve a speed up around 6 or 7 times with huge sequence length. So here, the red plot, the red bar, I plot two things. One is VSA with fine branch only, which is the actual block sparse attention kernel. And the entire red bar shows the speed up. Also, this slashed bar shows the entire speed up of the entire VSA attention. So VSA is composed of two things. One is coarse branch, one is fine branch. Fine branch is the actual block sparse attention, and the coarse branch is going to add overhead. So I think this performance is actually quite good because we are close to the theoretical speed up of 8 times. And one thing to take note that some attention patterns do not follow block sparse attention. They will include some elements that is not block sparse. For example, they may not have such speed up. And there are some other kernel implementations like flex attention, sparse, and they will have speed up as well, but they are not as huge. Yeah, by the way, we write our kernel in Thunder Kittens. Okay, so this comes to the ablation, and I can answer the questions about if compress will help. So there are many existing sparse attention in the field, but up till today, people still use full attention, even though they pay a high cost of 80% of the flops. But people still use full attention, at least in SOTA open source model. This is a very intriguing question, and we try to understand why. Here we are pre-training our video diffusion models with 120 million parameters. And we have two setups. So we run some simple experiments, scaling law experiments, to find a compute optimal budget. And we also overtrain the models. So this column, OPT, means if we train our models compute optimally, what is their loss? The lower, the better. And if we overtrain the models by 10 times the flops of the compute optimal, what are their flops? And we use the 1.2.1 architecture, and we pre-train from scratch, and we ablate with different attention. And one method is to compress the key and values. So if we can compress the key and values by average pulling them 2 by 2 by 2, so that is 8 times sequence length reduction. And note that we do not compress the query tokens. So we can effectively reduce the flops of attention by 8 times. And you can see that it actually converges very slow, and it has the highest loss across all the variants. And there are some very good sparse attention that is fixed pattern that can actually outperform full attention. For example, strided window attention, which we implement based on swing transformer. And some attention such as spatial temporal, which is another variant that people use a lot in like 3D VITs or like I think in diffusion models last year. You can see that in a compute optimal setup, they all outperform full attention. But the thing is, if we overtrain the model, full attention becomes the best. I think this partially explains why people use full attention, because people nowadays tend to overtrain their models to reduce the inference cost. And VSA stand out because it outperforms full attention in both compute optimal region and in the overtrained region. And there are a lot of components in our design. We are going to explain one by one why we want to make it that way. So one baseline we use is, instead of asking the coarse branch to choose which block to attend for the fine branch, we can force the fine branch to attend to only local blocks. And this is that's experiment 7. And we can see that a data-dependent trainable sparsity, which is experiment 8. So in experiment 8, F stands for fine branch, and L stands for like local. If we compare 7 and 8, we can find that data-dependent trainable sparsity wins over fixed pattern. And it also wins over full attention, as illustrated in the previous slide. We ablate whether should we include the output of the coarse branch to the final attention output at all. Because another design is to only ask the coarse branch to help choose which token to attend in the fine branch, but without including its output to the attention. So we can remove this OC and compare 8 and 10. So 10 is basically this graph, what this graph is showing. So we can see that including a global information from the coarse branch is necessary. We also ablate if locality pairs offer some schemes. So we can, for example, we can force this fine branch to choose its local neighbors, and then you can freely choose the rest. So we can ask, so this is the experiment 11. We can also add another like local branch here. Yeah, so those ablations experiments is very intricate, and for those who are interested, you can refer to the paper. And our conclusion is that we should let the coarse branch to freely choose which blocks to attend, and we should not add any local heuristics, such as those used in CAN. But global information is necessary, so we still need to include this output to the final attention output. And the last ablation is probably the most interesting one, is about the trade-off between block size and the performance. So here, this is how we map the cube size to the attention block size. And remember, this is the final configuration we use. And if we look at this table D, and we compare experiment 14, 15, and 16, we'll reduce the block size from 256 all the way to 64. And if we look at 18, we even lower the block size to 16 by 64, which is the smallest block size that is supported by H100, the WGMMA command. And we can see that, by the way, this table is flops controlled, so we use the same flops. We can see that the smaller the block we use, the smaller the loss it is. But if we measure the latency or the time takes to train such models as measured by the T-flop, so we write several kernels, attention kernels, with different block size. We can see that if we have very small block size, the attention T-flops is very small. That's why in the end we choose this setup of experiment 16. Because while the T-flops is slightly lower than 14, its performance is better. Yeah. And now all previous ablation studies are flops controlled, and we are training models with 128 million parameters. So to really show the effectiveness of our proposed sparse attention, we compare it to full attention on larger scale. So here, this is the loss flops for 410 million parameters models, and the x-axis is step, and we are using a sparsity of 87.5. So you can see that even with sparsity, VSA matches the loss of full attention. So VSA can train the attention, can enable a faster training training times of attention pre-training. And we even run sort of a scaling experiment where we train the models from 60 million parameters to 1.4 billion parameters. And we plot their plateau frontier, and here the x-axis is the flops. And we can see that this green line consistently achieves better loss flops plateau frontier compared to the full attention, and their line is like parallel. So we can draw the conclusion that VSA is more scalable than full attention. Another interesting question is, how do we choose the correct sparsity of attention when we vary the different sequence lengths. And our conclusion is that optimal, sorry, this is a typo, this should be optimal. Optimal sparsity depends on training budget as well as the sequence length. Basically, the more we overtrain the models, the more we want the sparsity to be low. This is very intuitive because if you consider that you have a model and you train forever, infinity, you would assume a full attention model will perform the best, right? So the actual, but in reality, when you train a model, you need to take into consideration the scaling law, and you cannot infinitely overtrain your models. So the actual interplay of sparsity, model size, and sequence length maybe requires another full sweep of scaling law experiments by adding the sparsity into the scaling law formula. And we leave that for future work, but we present some flops here for some intuition. For example, in this plot, we are varying the sequence length from 8K to 61K. And we observe that we choose the either top 16 or top 32 blocks achieves the best performance. And remember, a block has 64 tokens. So top 32, essentially we are choosing the 32 times 64, which is top 2K tokens. And you can see that there's no clear pattern about which top K is the best. Intuitively, we would imagine the K to be larger, the optimal K to be larger for longer sequence lengths. But it is not the case. The optimal K for sequence length 61K is even 16, which is even smaller. It seems that we are having a conclusion that for larger sequence lengths, we can even allow for larger sparsity. But here in this plot, we are flops controlled. So we are all training the 4 different rounds with the same flops. So a larger sequence length is less trained. It's very undertrained. So that's why we believe. And if we look at this, if we switch to a x-axis with flops, we can see that initially top 16 is the best, but it was later catch up in this region by top 32. And I would imagine this top 32 will later be catch up by top 64 in the future. And eventually, maybe full attention is the best, but it depends on how you want to extend your x-axis. And remember, this x-axis is exponential. So in practice, I think we should still choose a top K value that is like 32 or 64. Yeah, by the way, this experiment is already like kind of large scale, at least for academics, because for each round we are I remember we are running with 64 GPUs for like 1 or 2 days. So those are all the pre-training ablations for VSA. And I think this is the most practical things for people to play with, which is to fine-tune existing model with VSA. And we introduced 2 methods to gradually convert a full attention to a video sparse attention. So firstly, this compressed branch is newly added to full attention. So we inspired by LoRa, for example, we can initialize the coarse branch gate, its projection weight with zeros. So this term will be all 0, which means this here is all zeros as well. So initially, during initialization, we will only have this fine branch, and we can initialize the top K to full attention as well. So at the beginning of training, if we have in total 300 blocks, we can initialize the K to 386, and we will gradually decrease its value to 32, which is our ideal sparsity during the training. And in our experiments, we fine-tune one with synthetic data generated by 114B. This progress chart is very interesting. So this is if you look at it, at training step 0, if we use VSA with sparsity like with around 80% sparsity, it produces a video that is like with very artifacts, with many artifacts. But you can still roughly see the astronaut here, maybe. And then at the training progress, it's getting better and better. And then in the end, it can produce an actual video that is comparable to the quality of the full attention. And I can show some like models trained with our VSA and models with full attention. Oh, this is probably.
Yeah, you might be sharing something else, by the way, because I don't think we see your mouse anymore. Oh, okay, no, yeah, you're in the right place. Yeah, we just see slides, by the way. That's it.
Oh, you just see slides?
Yes.
Okay. Oh yeah, maybe I'll leave it to that. Give me a second. Am I right?
Yeah, works now.
Okay. All right. So maybe let me conclude first. So for video generation acceleration, the broad picture is that you can use many methods to accelerate them. I think the most prominent thing is probably distillation, because distillation offers like 5 to 10 times speed up. But as I just mentioned, the problem right now, at least in the open source world, with video distillation is that there isn't a lot of open source code, and it's scattered in different GitHub repos. And when people publish distillation code, they may only support one open source models. And then later you need to adapt it to a different models if you want to train your own. Like for example, people may publish code with Hunyuan, but later you want to train it with one. And the data for distillation is also a big concern. And for feature caching, it does not require training, but it only offers 2 times speed up. For sparse attention, I would say it also only offers 2 times speed up. But the pros for sparse attention is that it can speed up training as well. So for pre-training, if you can speed up for like 2 times, that's a lot. And there are other methods such as quantization that is also explored recently, like in sage attention. And we can also like similarly apply like FP8 linear and smoothing for video diffusion models as well, because they are all like all-in-all transformer. And we may also want to have some fused kernels for diffusion transformer, because diffusion transformer has a few, not so much, but different operators than language model. For example, the IDA-LOM. And our project, ongoing FastVideo project, try to build a unified and efficient training and inference engine for video generation models, where we try to support different models, different distillation techniques, and different sparse attention. And right now, we already support fine-tuning with sequence parallel, FSDP, and we support different models. We also support distillation with the PCM method. And we recently built an inference pipeline that has fast loading. We also have Tcache, we have STA, sage attention, and VSA. So we try to build a centralized place where people can submit PRs if they propose different distillation or like sparse attention methods into FastVideo to accelerate, because we believe there's a huge room to accelerate video diffusion models to reduce its inference time from 16 minutes on H100 to actual real time. Yeah, and this is some links. And thank you, and happy to take question.
Thank you so much, Perry. Yeah, folks, if you have any questions, like please drop them in chat. I'll read up some of the ones that we didn't go over earlier. Yeah, I guess we have the infinite view though. Like this, Perry, maybe we'll stop sharing your screen.
Okay.
I think yes, we can do this. Yeah. So I guess like my first question is like, I mean, as you were going through sort of modern diffusion architectures, it did seem to me like you could imagine that like, well, the ideal case is you distill down to a single loop, in which case like a diffusion model starts to look like regular LLM inference, in which case maybe frameworks like VLM could like do fast diffusion inference. And so I'm sort of curious like how you sort of think about the problems that are unique for infrastructure for diffusion inference versus LLM inference.
Okay, I think so. Firstly, I think it's convergent. Like recently, there are works, for example, Bagel from ByteDance. They are trying to build a model that can understand image and generate image in the meantime. That is quite similar to GPT-4o, which means we need to decode language model, and we also want to generate in diffusion. So obviously, a lot of code in VLM can be reused. And I think the major difference right now is that I think diffusion inference is actually, the problem is actually, maybe I will call it easier or like simpler than language model because it's compute bound. And maybe it requires more, for example, when you design like quantization kernels or something, you may, for language model, in some cases, you only, so long as you reduce the memory and it's memory bound, you can accelerate it. But for diffusion models, you really need to have a quantization methods that can leverage, like, for example, FP8 tensor cores to accelerate your model. And I think another characteristics from the application level is the enormous sequence length. I believe a language model, it can satisfy 99% of the use case with a sequence length of 100K. And yeah, maybe the last 1% of use case still needs 1 million sequence lengths. But if you look at the diffusion models nowadays, for 5-second video, you already need 100K. So if you want to scale up the sequence lengths, if people really want to generate a movie, that's really a huge problems to be solved in the future. To maybe with some linear attention, or maybe with some sparse attention. And in terms of yeah, and is there more things? And diffusion models, maybe this is something like that's similar to RL, maybe, that you need to host multiple models for your diffusion pipeline. For example, you need to host your language model encoder. You need to host VAE and diffusion models. And when that comes into like parallelism, how do you like shard your models? Do you want to have disaggregate the language encoder and the diffusion part, or do you want to like put them in the same card? That's also a question. And I think there's a lot of room. And nowadays people are just like starting to explore those things. And there isn't maybe there are many directions. Yeah.
So speaking of the sort of future directions, one paper I enjoyed reading yesterday was the hybrid flow paper, which was a paper on it's a paper on Virl and RLHF infrastructure. And so like one of the things they talk a lot about in that paper is basically how different like models might have different like sharding strategies. And obviously when I looked at a diffusion model, it's not like a model, it's like a diffusion, it's like a list of models, and it's like infrastructure. And so have you also sort of seen ideas borrowed from like modern RLHF infrastructure start to make their way towards diffusion modeling? Are people now using Ray? Are they using other products?
Yeah. I think there's one paper, is it published in NSDI or OSDI, that they basically put the language component into different GPU card, and then it's sort of like deserve that this, it's just like this aggregate the language component and the diffusion. So diffusion is like the prefill of language model. Yeah, and we haven't explored that in our FastVideo project yet, but I think there are some works coming out.
And so sort of similarly, again, speaking of convergence, presumably there's some labs experimenting with MOEs with diffusion models, and this adds other important constraints, I think, as far as how you design things like FastVideo.
We haven't touched MOE yet, and in FastVideo, I think one thing that that is different from like existing. So people right now, I think they mainly use diffusers for inference, and I think diffusers works okay for like it already works okay because diffusion is compute bound. All you need to do is just add a torch compile and it runs pretty well. And one thing we do that is different from diffusers is we have so we break the diffusion pipeline into a different stage, and we try to reuse code as much as possible. And we also borrow a lot of code from VRM, so which means people can contribute different kernels and attention kernels, and it's very easy for people to add attention kernels because attention kernels is, as I just said, all my talk is about attention, and it's very important. And we try to have something that is, so if people contribute attention kernels, it can be automatically used across all different models. That means we need to reuse code by a lot. And I think that's the main goal that we try to achieve here.
All right. I think I see maybe one last questions we can go through. So this question's from Acyclics. Would importance sampling make sense here? Maybe if one course attention block is more important than others, more fine-grained sampling should be done for that block. I forget which slide this was referencing. I think, let me remember. This was like 20 minutes ago. Yeah, maybe we can pull up your slides. It'll be easier to remember. I think it was maybe slide 20.
I'm not sure what exactly is he referring to by importance sampling. Like, is it like different blocks use different kind of attention, or different blocks use different like sparsity level or something? If
I'm not sure either, to be honest.
Yeah, let me just presume. Yeah, I think it's definitely a very important question to assign different sparsity level for different blocks, or maybe even time steps. And those are some heuristics. And when we do a lot of this pre-training ablations, we want to keep things simple, and we use a uniform sparsity across each time steps and different blocks. And even for our pre-training experiment, we use the same top K. We use the same K for different time steps and different layers. And I think adding different sparsity for different time steps would definitely help. And there already have some heuristics. For example, people like some other works, like for sparse attention in video generations, they would use full attention for the first few time steps in the diffusion process, because a heuristic is that for the first few time steps, it's more about global structures. And once you fix the global structures, then you can use sparse attention for the rest of the diffusion time steps, and that wouldn't drop your quality, and you can produce videos that is very similar to the original videos produced by full attention. Yeah, we didn't explore that because we want our like sort of experiments to be more principled without a lot of confounders. But yeah, it's definitely worth trying.
All right. I think with that might be a good time to call it. Perry, thank you so much for joining us. Folks, if you have any more questions to Perry, I guess you can find him on the FastVideo GitHub, and I think you're on the server as well, so feel free to tag him there if you have any follow-ups. And yeah, thank you so much. We'll see everyone soon.
Thanks. See you.
Everyone.